Okay. Thank you all for joining. My name is Ariel Moulet. I lead the community engagement team at Sophia Science Center. Today is our last installment of our Pipeline Week series. We have Dario Fata, who is instrument scientist for FIFI-LS, who is presenting us the process for data reprocessing through the pipeline for FIFI-LS data. So, reminder that this meeting is recorded, so we will put the link on our website shortly next week. And if you have questions, please put them in the chat, and I'll interrupt Dario when it fits well to let him know. Dario, you can go ahead when you want.
Okay, I'll try to share. See if you can see the stuff.
Yes, it's not full screen yet,
Yeah,
but we can see the stuff.
Okay, now it should be full screen.
Perfect. Yeah.
Okay, so welcome to this little chat we'll have about the pipeline. Not only the pipeline, but a little bit everything related to the reprocessing the data. So this is the last series we had in Chile. So we took a picture of our team in front of the telescope in front of FIFI-LS. And if you never heard about, I hope you heard about this kind of data of FIFI-LS, but if you never heard about, I will talk a lot about the spectral cubes. So immediately I will show you what's a spectral cube. Spectral cube is simply a series of images taken at different wavelengths. So we can take one of these frames and see, for instance, this is the antenna galaxy interacting in a certain wavelength, or we can take just a shot through one of the pixels of this image and having one spectrum. So this is what we are talking about in this talk. And briefly the outline, so we'll talk about the basics that you have with the FIFI-LS data, then directly how to install the pipeline, how to get the data from the archive, how to run the pipeline, and finally something about checking the results. Okay, immediately, what's the basic of these instruments? Of course, I say there are spectral cubes as a result of the observations, but for each observation we have two different spectral cubes because the instrument actually has two independent gratings in two different wavelength ranges. So one is the so-called blue channel, which goes between 50 and 120 microns, and the other is the red channel, which goes roughly between 120 and 200 microns. There is a little overlap in between the two, which allows to observe one line in the two. The two channels have a slightly different size. So the pixel in the blue has 6 arc seconds and the pixel in the red has 12 arc seconds, which reflect more or less the spatial resolution. And I will talk about in this talk a lot about spaxels and spaxels. So in this jargon is simply to say a pixel which corresponds to a pixel on the sky is called a spaxel. A pixel could correspond to the pixel on the spectrum is called a spaxel. So if you can see how the instrument works, essentially you have an image on the sky which is first sliced in 5 pieces, and then every one of these slices is dispersed along the spectral dimension. So for every single pixel in the sky, we have a kind of an instantaneous spectrum of 16 pixels in the spectral direction. Then the pipeline will recombine this in a cube. It's interesting to see how these spaxels, or spatial molecules if you want, appear on the sky. The instrument in theory should have them completely uniformly separated by 12 arc seconds and 6 arc seconds in red and blue respectively. But what happens that as everything in the world, nothing is perfect. So the different slicers that slice this image actually don't work exactly like that. And there is a little bit of inhomogeneity in the distribution of the pixels on the sky. So what we can see here is the pixels in the red are the red channel, the pixels in the blue are the blue channel as they appear on the sky. There is a shift also in between the center of the blue array and the red array, as you can see. So when you observe one object, you can center either on the red or on the blue. If you're more interested in covering this in the blue channel or in the red channel. The other thing that one has to take into account is that the illumination on this pixel is not uniform either. There is actually a column that is kind of not well illuminated, and this is reflected when you do the floods for every pixel. So what you can see here is the spatial flood, if you want, for many series, and these are different colors. And you can see that the pixels that are numbered 10, 5, 10, 15, 20, 25 are much less illuminated than the other. In fact, we have to apply like a correction of between 0.4 and 0.6. And this means that these pixels are a little bit more noisy at the end. Okay, the other things that you have to take into account when you do this is what is the instantaneous coverage? The instantaneous coverage is, as I said, the spectrum that is taken every time you made an observation by the 16 pixels along the spectral wavelength. It is possible to cover more by moving the grating of the instrument. When you move the grating, you instantaneously cover another wavelength range. But as you can see here, I put what is the instantaneous coverage at different wavelengths, which of course changes because we have a variable instrument. And what is the unresolved line width? So you can see that one line is, if it's unresolved, is well covered by the instantaneous coverage for every observation. A little bit of grating dithering is usually done also for any observation, like 2 or 3 different positions of the grating are taken to have a little bit of oversampling and a dithering in the spectral direction. One other things you're probably interested is what is my PSF when I observe some object with FIFI-LS, and what is my spectral resolution. These two plots give you an idea of what is the PSF of the point source on the FIFI-LS, and these are actually taken from nowadays I have more measurement, but I didn't add them, but these are taken from real measurements of point sources, and you can see what we have for the main lines that are observed with FIFI-LS in the different orders. What is essentially the width of the PSF, and if you have a point source, what is the flux fraction that is supposed to be in the central pixel. This can be useful also when you do proposals eventually to evaluate what will be the flux seen by one pixel. Then spectral resolution also changes with the wavelength, and this is the diagram that you see. So you can see that the spectral resolution can be kind of medium spectral resolution, they say, typically around 1,000 or 1,500 in different ranges. Oops, okay, I think I clicked something more. Okay, that's it. So the next stuff I want to show you is the basic far infrared line. So you probably, I don't know how familiar you are with the far infrared, but these are the lines that typically people observe, and especially when you observe extragalactic objects, it's almost impossible to see other things. But these are the line of oxygen, nitrogen, and carbonium that are typically observed. And so I give a little table where you can see what is the resolution and what is the instantaneous coverage in kilometers per second and micron. And this is one picture that I took from a paper where different galaxies, the spectrum of different galaxies is shown with the different lines that I put in this plot to show how intense they are. Of course, we see that immediately that the most intense line is the famous ionized carbon, which is essentially the kind of workhorse of FIFI-LS, and which usually gets like 1% of the total infrared flux. And the second one is the O3, you can see, and then the other ones. Okay, so now let's come to the subject of this talk. Why we have to use the pipeline when in the EARS archive we can find all the level 4 data ready for our science. This is true. There are a lot of data already processed, and we try to do our best when we process, but we do this in a general way. So we use a pipeline with parameters which are typically good, more or less good for any type of science, if this is a point source, if it's diffuser emission, and also taking account that different series been taken in different years, the pipeline has evolved. We try to reprocess, but we could not reprocess everything for every change of the pipeline. And also the calibration has changed with the time. We improved actually the calibration. We started to do measurement in the laboratory to have better flux, and we accumulate more and more um, flux calibrators, so we improve the calibration in flux. And also there is a change that happened in the instrument where we essentially change the window, the filter window, and this changed a little bit the sensitivity. So all these, you can see there are some advantage in reprocessing the data. So the first I already say. The second one is that you can combine actually data from different observations or different proposals that observe a same object in different ways and have a better image or have a better spectra. And or you can combine even from the same series where people take different positions, which we are not combining at the end because sometimes they don't overlap well, but for your science could be beneficial to put stuff together. And also you can be just more picky and wants to reject some files that are being included but actually have higher noise, so probably you can have a better result at the end. Or finally, you can resample the final data with a different smoothing parameter. So in this case, you can press, for instance, if you're very interested in point sources, you can really use the parameter that allows you to recover fully the PSF of the sources, or if you're more interested in diffuse stuff, you can use a parameter of smoothing which is bigger, so you have something which is less noisy. Now, on Tuesday, Melanie already talked about how to install the pipeline, so I'll just give you all these URLs, URL addresses in one PDF, so you can once I put the PDF, you can just click on them and go there, and I'll say I suggest to install a type of installation which is essentially using the edit mode in with pip. So what does it mean? First of all, if you want to use this, you need Anaconda Python, so you have to install it, and I give the link to install it. Once you are done with this, you should create an environment for this installation. So Sophia has created an environmental file, or a YAML file, that you can grab at this address. Once you have this, you can actually create an environment which contains all the things necessary to run the pipeline. You can activate this environment with this name, and the environment is called Sophia_Redux. That's the name given. And once you've done this, you just clone the entire repository that we have in GitHub of the pipeline. Once the repository is cloned, you can install with the pip install using the -e, which is essentially edit mode. What does mean edit mode? It means that if there is some modification in the pipeline, you simply, let me see, too fast. If there is some modification that happens in the pipeline because we continuously update, for instance, calibration or some other modules that are, we'll find better ways to do it, we just go into the repository and we do a git pull. At this point, we have all the new stuff. And since you are in edit mode, the next time you start the pipeline, you immediately activate all the changes. So this is an advantage. The other way you have to do this installation is using directly conda install. Of course, conda install grab the latest the latest pipeline that has been uploaded to Anaconda, which usually, I think Melanie tried to do a good job and update very often, but it will be not done immediately after the calibration is uploaded. So it will be done every few months. So it can be actually, you're getting a version which is not really completely up to date. And the other advantage is that if you find some errors in the pipeline, if you want to do something different, you can actually go into the repository, your local repository, make your changes and try them. Of course, if you just install the Anaconda version, you cannot do this, or you can do that, but it's very complicated. The other things I want to advertise is if you are using this pipeline, you find something that doesn't work, or you have some suggestions, or you want to understand something better, you can just communicate with us directly through GitHub. So for this, you need, of course, an account in GitHub, and it's absolutely free and easy to open one. And once you have it, you can just submit a new issue. There is when you go in the GitHub page of Sophia Redux, there is a part with issues, and you go click on issues, and then you have this appearing, and we have the issues that have been submitted, and you can submit a new issue. So you open a new issue, you write your stuff, and then submit. If you find out that you did some changes in some modules, or there is something that you find out is wrong, you just submit a little snippet of the code, and it will be considered almost immediately. That I know because Melanie is super fast in considering stuff. Let me see if I skip the stuff. Okay, this is not all for FIFI-LS because once you install the pipeline, you still need to have the model atmosphere that are used for the atmospheric correction. So what I suggest to do is downloading this library that we created, which is kind of fine library, and consider different water vapor measurement, or water vapor values, sorry, and different altitudes, and essentially a grid, and this can be used to process the data, taking into account the water vapor that is observed and conserved in the header. Okay, now we arrive at the part of how I get my data. That's happens through the IRSA archive, which is hosted by Caltech, and you have the little URL on the bottom. Probably you are familiar with IRSA if you ever did any infrared observation, because IRSA contains many other missions like Herschel, Spitzer, and so on, WISE, and voila. And so it works more or less in the same way as the other one. So we can, when we open our Sophia search, we have a search tab where we can put, for instance, the name of an object, and then we can check, for instance, the instrument we want, and we can check also the processing level we want, and we just submit search. So if you do like that, and you submit only level 4, you can get, for instance, in this case, I submitted one galaxy that we published recently, and what you find is one AOR that has been associated with this observation. And so what you do, you can play here. Here I put something better. If you do hypes, you can actually get a color image of the galaxy, which is nicer, and an approximative size of the coverage of the observation. If you want to grab everything, you just go in the AOR, you click AOR, and you have you click prepare download. At this point, you have a pop-up window that come up, and it starts to grab all the stuff that is. So in this case, was 8 of 656 completed. And when everything is done, something will pop up and say, save this. It will take a little bit, so be patient. At the beginning, I was thinking that nothing was happening, so I was reloading and reloading. But wait a moment, and you have something coming up. And when this is done, blocked, okay. sorry, because okay, when this is done, what I did, I grabbed this data, I unarchived and untar them, if you want. So I go in my downloads, because this is where usually the data are downloaded, and I found out this file. To be more clean, I created a directory, and I unzipped this stuff here. And on my computer, I actually downloaded a program called Tree, which allows you to show the directory tree in a very nice way, and this is what you get. So that's kind of a complicated tree, if you want. Oops, sorry. Very complicated tree, which shows that this data come from Sophia and from FIFI-LS. Up to here, we are okay. Then there are two branches. One is the level 4, so the data that are being highly processed. And you go here, and you see this is the processing number. So every time we process something, our system gives a number. And then we have the data. The data contains groups. And each group, in this case, is very simple. A group, there are only two groups. One group corresponds to the red channel, and one group corresponds to the blue channel. So we'll find two different FITS files that have essentially the spectral cube. On the other one, we can see what happened. This data comes actually from one particular observing cycle, which was the 6U, and from one particular flight. So this is the flight 551, which happened during this date. And again, here we have something which is processed data and archive data. Why we have processed data? Because sometimes there are many different directories that contribute to the final cube. So in this case, it's just one, so it's a simple case. And again, we have the processed data and calibrated data, same structure as before. And here in the raw data, so we have something slightly different. So we have the raw directory. There is a revision name, and this happens because many times the header have some error or they're slightly corrupted, so we have to correct them and re-archive the raw data. And we go inside the data, and this is something done directly on the plane. We have one folder here, which is called folder 4, and this comes from the fact that sometimes there are crashes crashes of the software during the observation, so we have to open new folders every time you restart the instrument. And finally, we arrive to data, where you find all the data. You probably don't want to go through this to this road, because you get a lot of data when you grab all this reduced data plus the raw data. If you want to adjust the raw data, is slightly simpler. So you can just grab the level 1 data in this case, and you can specify the FIFI-LS. And remember to get a radius which is bigger than the default, because the centers of the raw data sometimes are farther off from the target. And otherwise you finish like me. I put the default, and when I grabbed this, I had 0 data, which I was very perplexed. Then there is this instrument constraints. You can see that you can configure the instrument. Okay, that's spectroscopy, but for the moment, there is a bug in here that prevents you to select which spectral elements you want. So you cannot choose the red or the blue channel here, otherwise, again, you have 0. But if you do any, you get the 2, and what you can do later is going through and just filter the one you want to select. So what I did here, I put essentially star LW fits, which means LW stands for long wavelength, which is the red channel. SW is short wavelength, it stands for the blue channel. So in this case, I wanted only to get my C+ data on this galaxy, so I just filtered on the star LW. And then I downloaded, and voila. Here you can
Dario,
even...
can
Sure.
I interrupt you 1 second? Is it possible to process the red and blue at the same time in the pipeline, or you should always do it two separate processing?
Okay, no, the pipeline process one channel at a time.
Okay.
Here is just downloading. You can download everything, and then you'll just do this process one at a time.
Okay, thanks.
And yeah, there's one thing here, include file type. So you can include, by default, include the PNG, which is simply a kind of figure of the of the of the line, but you don't have to do it. So you can just unclick. Once you have this, the tree is much simpler. Essentially, is what I have for the raw data. And you see, in this simple case, the whole data is 2.2 gigabytes, while the raw data is less than 1 gigabyte. So clearly, raw data for the RAD. So clearly, you save some time for downloading and finding stuff. And also, if you don't have a lot of space on your computer, this helps. How they are these raw files? So you see a lot of files which have very strange names, and these are kind of the file that you find in this specific example. And you'll see that there are several numbers. So the first number relates to the files taken during a flight. So they are usually in progressive number. Then we have the UCT time of the acquisition. Then this relates to the observation. So every observation has an EOR that correspond to the observation, and this is as a number of scans that are presented here in a sequence. Then there is the target name. Then there is one part called ACT, which is essentially one specific EOR related to the program. So for instance, some programs want to observe a same object in two different bands, so we have two different ACTs. Then we have two parts which has offsets. So if you have some dithering around the central position, you'll find the offset arc seconds here. Then we have the node. In this specific case, we have a noded observation. So we have a node A and node B. Then finally, we have the channel. As I said, it can be LW for long wavelength or SW for short wavelength. So the red and blue channel respectively. And then, of course, there's a fits. Each file contains all the readouts for a certain number of grating position, and only for one channel. In fact, they have different labels for them. And let's go on. Oh, at this point, I have prepared a Python notebook because so you can actually download this Python notebook when you have this set of data that I use in the example, and to show you something a little bit more engaging, hopefully. So I will stop sharing and try to share the Python notebook. Should be here. And I hope you can see it. Please, Ariel, confirm. Hello?
Yeah, we
Okay,
can see
perfect.
it.
So
No
can you
problem.
see this? Okay, great. So I created this little notebook just to have something slightly different and to explore a little bit this data. So I hope you are kind of familiar with the Jupyter notebooks, and which are kind of a fun way to interact directly with Python. So in this case, I show you how these files, the raw data, are organized, and you can see this. I just open one of these files and do the info for this specific file. So you can see that there is a primary extension and another extension which has a table. Okay, so the first thing I would like to observe when I download file is there is a wavelength value associated with this, this has been added to the headers or not. We tried to add it, but I think we are going backwards, and now I think we are at around the fourth cycle. So sooner we'll have everything inside, but the older cycles still don't have this keywords inside. If you want to check, so just grab the header as I did before and print this field. In this case, it's present because it's also a recent observation. Then what you can do is check some parameters that are available in these files. So you can simply, what I did here, I did a glob or my directory. I grab all the files which have LW as end, which is essentially what I downloaded. And I went through this and I capture in the header all these keywords which are telling me what is the altitude, what is the water vapor, what is the zenithal angle, so the elevation of the telescope, and the date observation, and latitude and longitude of the observation. So I just go through this stuff, I order and I plot, and what I found out, first of all, is I want to see what is the size of these files. Simply from the size, I will see if there is some file which is corrupted or not. There are two files, in fact, in this directory, which have a size which is smaller than the other, which means that not all the ramps of the observation have been recorded. So this file should be rejected, and we'll see later that they appear again as bad files. So this is the first thing you have to know. When you get the raw file, you get all the files, so also the bad files. So you have to learn how to get rid of them. Then I put in one plot what is the water vapor, the observation, what is the elevation, what is the altitude in feet. So we see this is a good observation because it's been done at a very high altitude, like 43,000 feet. And the water vapor was very low. And this is the elevation of the telescope. You see, I put two little dotted lines in red, and these are the lines that essentially are the limit of the elevation that we allow to the telescope. Because if you go slightly higher or slightly lower, we intercept essentially the end of the door of the plane. And this means that we are adding vignetting to the data, and the data are bad. So we want to reject this file. Sometimes, by accident, some of these files are taken. So it's always a good thing to do, checking if some of these files happens to be there. So if by chance we went a little bit further on. In this case, my experience is reject this file immediately because they just add noise to the data. Something fun you can do is seeing where these data are taken. So for this, you have to actually install on your Python distribution Car2Py that allows you to show where Sophia was flying, where it get its data. So this is like the fun part. We see where it started and where it finished. So we see that actually to take this data, Sophia flew on the Pacific, just out of California here, and went through the south. So I talk about ramps. I don't know if you are familiar how the data are taken in the infrared, but what is essentially done, we check the voltage every few fraction of second, and do this to build a ramp of voltage. And then at certain points, the detector is reset and we restart the process. And you can, I did a little script here to just show what the ramps are. So you see this as a function of time. We go and get these 32 readouts and then reset another 32 readouts and so on. From the slope of these ramps, we can infer what is the flux that is hitting the detector. So this is essentially the data in the most pure form, so the voltage measured. Of course, as I said, you have to measure the slopes. So I did a little code here, which is very, very simple. Don't get scared. It's just that I have to rearrange the data in a way that I can actually use them. And in this specific example, there are 3 different grating positions for every one of these files. So which means that one grating is left there for a while. Many ramps are taken. Then the second grating enters, and the third grating enters too. And so this happened for all the plots. So what happens is that if I took one file of them, and I left you also as an exercise to go through the bad file to see what happens. If you get one good file, I'll see that there are, for the central pixel, I will have some volts per second here, here, and here. And this is because the same pixel now sees slightly different wavelengths since the grating position has changed. So we'll see this kind of stuff because we are going essentially through the SED of the object. If I do this for all of them, you can see that this is much more clear now. So we have the three different grating position for the same pixel. So I see what happens during the observation. And so essentially this is telling you what the telescope background is doing, because usually the signal is a very small fraction of the telescope background. You can see that the telescope background is pretty stable. It goes a little down there, and this can be simply that the water vapor is improved, so there is less background. And at a certain moment, it seems to go crazy, and then it restabilizes. So yeah, the first thing you think is, oh, perhaps I should reject these files because they are very bad. Remember that for every single one of these observations, we have one observation on the source, one observation of the source, so what's called chopping. And it happens that all the points are actually inside these bars. So these are ramps from the two chop nodes, for the two chop position. So what happens when I subtract the background? You see the same data now are like that. So we see that the crazy ones are probably slightly more noisy, but they are very, very similar. So my advice in this case is try to do it without rejecting this very noisy one. And then if you see this is really bad, you can try by rejecting the other one. So this is what I had to show you for this exploration of the raw data. So I go back to my presentation. And we can go, okay, we can go through the running the pipeline. How the pipeline is organized. The pipeline is written in modules that are applied sequentially. Every module has some option that you can select, and then you can save actually the products from each step, and you can save and eventually inspect them. Some of the modules which are particularly intensive as computation can be run in multi-threading, so they can speed them up. Of course, I put a link to the Melanie Clark presentation of the other day, because she showed how to run the pipeline through the GUI. I will not run the pipeline through the GUI because I am a command line person, so I will show how to do it with the command line. And, oops, okay. Of course, you have to run the pipeline once you install. You have to always remember to activate the environment, and then you have to run these simple things: the redux underscore pipe -c, which stands for configuration redux parameter, and then a list of files you want. The list of files, of course, you grab from you just do an ls or whatever you do to create a list of files. Then you, from the list of files, you take out the one that you consider are bad, as we see in the previous snippet. And now the only thing you have to do is going through the parameter configuration, which is a little bit the most tricky thing. So in the parameter configuration, which I can actually give this parameter file as another product to add to this presentation, but you have all this printed here. You can see there are several steps. We can, at the beginning, we can actually say exactly which modules we want to run. So if you, for instance, we want to just run the first three modules, we can just put the recipe all like that. So just put in a list of the modules. If you don't put any list, every module will be executed. Then for every module, we have the list of the parameters that we can put. So in some cases, it's really simple. You want to check the header, yes or not, so true or false. You want to save this specific one, you put, yeah, true or false. So if you don't want to save every single parser, you just put false, false until the end. In some cases, you have this parallel through, which means are we going to use several cores at the same time to run this faster? So there is some multi-threading going under the essentially under the when the program is running. Then there are other parameters that are kind of fixed by default. You can be more aggressive or less aggressive. This is when you fit a ramp, for instance, you can decide what threshold you wanna use to reject bad ramps or less. And we put some values that we consider good, but you can always do your tries. Here, this is the bad pixel file. If you don't put anything, is the bad pixels that is considered from the pipeline. So this is another calibration file. If you think that you want to reject more bad pixels, you have to build your own and essentially copy the one that you find in one of the directory of the pipeline and reject, for instance, more or less pixels depending on what are your tastes. For instance, someone wants to reject all this column that is bad illuminated. If you have a lot of data, you can do this, and probably your result will be slightly less noisy. Then you have other options, and this is I advise you to leave this as they are, because this essentially is rejecting the first readouts of the ramp, and which are always bad. And this is subtracting one of the engineered pixels, because we saw that this reduced the noise enormously, since there is some correlated noise in the instrument. Then, okay, we have subtract chops and combine nodes, which are pretty evident. So subtract chops is subtracting the sky position from the source position, and combine node is, I don't know if you have any idea of this chop node observation are done, but essentially what you do, you put the telescope first on the source and chop it on the sky, and then you move the position which was originally on the sky on the source, and you chop with the other on the sky. So this essentially allows you to combine the two telescope paths that are done during the two observation with different chopping position. So without going too much in the detail, that's pretty simple. And the only thing you can do is, instead of going to the nearest, which is actually the one that makes sense, you can do some mean of the other positions. The off being is technical, is more for calibration than, so you shouldn't be worried. Just leave it false. Then there are the calibration part. So in this step, the wave calibration is applied to the data. So from simple grating position, you pass to real wavelengths, and this is done through calibration files. Then the astrometry is added to the data. So this is slightly more complicated to do. The only parameter you want to really take into account here is, do you want the final cube oriented with typical northeast orientation, or you want do you want to have a cube which is actually the image which is rotated according to the rotation of the array with what the observation was taken. So sometimes we rotate the camera, and we can take, for instance, all the observation along a particular direction. So sometimes it's let's say you can have smaller cubes if you just go with the direction of the array, but the disadvantage is that it's all rotated, so at the end it's kind of difficult to make comparisons. And actually it doesn't make any real difference, because everything is simply interpolated, so you don't lose anything by applying the northeast observation, just to have a bigger cube. Then we apply the flats. I just put a note here. We don't apply to compute the errors, if you want, on the final flux, and this is another chapter on the reduction, if you want. The error on the fit of the ramp is propagated through all the pipeline. So one step we should which should be done, is propagating also the error that is done on the computation of the flat. It turns out that this error is pretty high because we don't have an infinite number of hours to do the flats. So we don't want to propagate this error, otherwise the error will be simply enormous and essentially systematical. Then we combine different grating scans because we want to have a simple spectrum at the end, not several spectra. And then we arrive at the part which involves the telluric correction, so the atmospheric correction, if you want. So here you have to put the path that you use to untar the library of Atran models. And then you decide the cutoff. So typically we put 0.6 or 0.5 in the pipeline to cut the fluxes that are taken in region of the in wavelength regions where the atmospheric correction is actually too big. So the transmission is lower than a certain value. So in this case, it's 0.6. And this because when you have such a low transmission, what happens is that most of the flux is highly noisy, and the result actually don't make any sense. Finally, use...
Dario, if I can interrupt, just
Sure.
up until atmosphere considerations, do you find it typical that you need to change the configuration file from the default, or
No, usually
okay.
not. But the only thing is if you want to rotate, for instance.
Okay.
That's the only thing I think is useful. The other thing I advise not to change because, yeah, it's your own risk. As I said, that's use WV equal true means if you use your Atran model. So this allows you to actually read the observed wavelength, the observed water vapor values in the header. If you don't put it this, they will not read. And a typical correction will made using essentially the altitude, so the expected water vapor at the altitude. So this is not what you want. This is important. You put true. Then we have the calibration flux. That's also, you have to use it. If you want to have another calibration, you just have to define another response file. That's what it's mean here. And then there is the barycentric correction. Finally, we arrive to the most important part, which is the one that where actually you want to do some changes if you are rerunning, because your science needs could be different. So this is the part which essentially do the resampling of the sparse spectra we have into a cube which can have any resolution you want. So it'll be, of course, interpolated in some way. And what the pipeline does is to use a kernel to go through this data, and the kernel that is at the same time as in the spatial dimension and the spectral dimension. So you see that there are two parts here, which one is essentially the kernel you chose in the spatial dimension, and one is in the spectral dimension. The two are applied at the same time. And okay, we have something at the beginning, and this is still experimental, will become in the next pipeline. I just put it because in preparation. The pipeline for the moment uses just half of the cores on your machine, because otherwise it usually needs a lot of memory. It can crash your machine. So on my request, Melanie added the possibility of using more cores if you want to be more efficient. But it's a little bit of your risk, because when I tried with all the cores on my machine, I just crashed my laptop. But she added also some other things that prevents to use too much memory. But this would be the next version, which will probably come in a month. There are other things here. For instance, the most interesting is weighting. So when we use all the data, you can choose to weight using the errors or not. So you can use simply all the data, or just weight and weight less the data which are more noisy. So the fluxes are weighted by the variance essentially of the RAM fitting. Then then we have the special choices. There are some things. So the first one is the oversample. So how many times you want to sample the this is the that you have. It has nothing to do with the resampling. Simply here it doesn't change anything in your resampling. And then we have the the parts that actually go through the kernel. So we have important things are the smoothing. So this is essentially the size of the of essentially the let's say the width of the kernel that you are using. So if you put 1, this means that you are smoothing with a kernel which has a width similar, okay, actually equal to the PSF of your data. Of course, putting 1 is a choice that will slightly broaden your data, as I will show you later. Then there are things like the window. So this is up to where you want to consider data. So in this case, is a 3 times the FWHM of your PSF. You can put less, and this is just essentially will be faster in computing. And finally is the edge threshold, and this is how much you want to discard the threshold. Since the threshold, sorry, how much you want to discard at the edge of the field. Since we are using some interpolation, of course the edges will have border effects, and the border effects can be dramatic. In fact, sometimes you can see that there are kind of fake sources just at the border of your field, and never trust them. And you can choose to have a higher threshold to reject stuff, but that's your own choice. I'll come back to this slightly later. And we have also the same stuff. It can be in the spectral side. The spectral side, we have a much more differing, much more oversampling than what we have in the spatial side. So it's slightly less. You don't need to smooth so much. In fact, this is typically the choice is half of the window, which essentially conserve perfectly your spectral resolution. You see, we have just 1/4 of the window for smoothing and one half of the window for considering stuff. So essentially, you don't lose anything with this because we have so much redundancy. On the spatial side, the redundancy is very not so high. So this is a choice that can actually change a little bit your results. So if you smooth too much, you remember that if you have peaks sources which are like point sources, you are smoothing them too. So the total flux you are in an aperture will be smaller than what is should be. A possibility is using the adaptive algorithm, which is included here. Of course, if you put none, you will not use it. If you put the other ones, you use it. And I'll show you that's it helps a little bit. And this is kind of, let's say, the adaptive algorithm allows you to rescale the size of your kernel depending on the flux that you find. It's not a perfect, I think, solution, but better than nothing when you have a kind of variety of uniform and peak sources.
Dario, I should give you a heads up that we have 5 minutes left until the top of the hour.
We are almost done.
Okay.
So this is essentially saying what I already said, but I wrote because someone will read these slides. And I think I will say a little bit about what we get when you run the pipeline. Of course, if you start saving everything, you will have a lot of files, and you recognize them because they have different labels. And these are the labels that you have. The one that you really want is the WXY, which is the final cube resample. The other are intermediate product that you can see. The WXY file will have several extensions. So if you go and explore what is inside, you see it's pretty complicated. You have several extensions. One will be the final cube that you really want with the fluxes. One will be the cube before the correction for the atmosphere, and then you have the atmosphere itself and many other things. So what I advise you is if you want to do an inspection which is like user-friendly, don't go through a notebook Python because it will become really complicated. So I wrote a code which is called sourcepex. You can see here how to get it, how to install it. You can install this through Anaconda. So it's pretty easy to install, and voila, and all the instruction there. So what you have, it's when you open a WXY, you can immediately see on one side the image, and this is not really the image, this is an optical image, sorry. And on the side, you see the spectrum for the position. In this case, what I did, I grab an optical image, and you see on the top we have some tabs that show the flux and uncurated flux, the coverage, and finally this optical image that I downloaded. And you can overlap the contours and see from this point here, we have this flux here. I think I skipped one thing that I want. Yeah, that's the oversmoothing. The oversmoothing is that what I was saying before. So what happens is that if you have a kernel which is too wide, and you apply to a portion to this data, you can see that on the top of on this region of the galaxy where you have actually the most pointed emission, I compare what I get with the smoothing one, so the kernel width equal to the PSF of the image, and the kernel which is half of the width. And you see that the half of the weights recover much more flux than the one that's essentially broad in the figure. And so I did also experiment with the adaptive kernel, and they came very close to this 0.5 FWHM. So this is more or less what I now use in the reduction of the new data, because these consider much better the resolution of the data. Although it's a little bit more noisy where you don't have so much signal. So going back, so that's what I was just advertising Sourcepex another time, and this is what you can do. For instance, you can define an aperture and then fit the line and having what is the flux. So, and there are many other things, but this is not a talk about this. So if you are interested, we can have another complete different meeting just about analyzing data. And this, I think, is my last slide.
Thank you. That was really full of details, and thanks for Suspects. I use it for other stuff too, and it's pretty neat.